Okay, good afternoon everybody. So we are going to have 2 hours today about continuous variable quantum computation. So the first hour we see what this is about, the general operations and the measurement-based model. We are going to revisit it. And in the second hour we are going to deal with error correction, and in particular GKP error correction. So this is the plan. So I will not go into the formalism. I put in the notes, like in the appendix, an extensive coverage of the main formalism. By the way, the appendix is due to Pontus. And probably all of you know already that we are not going to talk anymore today about qubits, but about the quantized harmonic oscillator, which is a system that models, for instance, quantized electromagnetic radiation. If you confine the light in a cavity, then the modes that the light can take. So the light must be reflected at the border of the cavity, and then you have only specific quantized modes. So this would be the first one, then you have the second one, and so on and so forth. So these are each associated to an energy level, which can be expressed in terms of creation and annihilation bosonic modes. And then associated to the quantized electromagnetic radiation, there are quadratures of the field that are Q, A plus A dagger over square root of 2, and P, A minus A dagger over square root of 2I. There is arbitrarity on how people define this, whether they take square root of 2 or 1 at the denominator or 2. So 3 different conventions that do change a lot in the calculations. And of course, 1/3 of the authors roughly chose one of the 3 options. So it's quite messy in the literature. But we are going to try to stick to this one. And these observables have a continuous spectrum. So they have eigenstates that are unnormalized states, in the sense that they correspond to our infinite energy that satisfy the following eigenstate equation. So one can use different conventions, and probably we are going to use several of these, but for the eigenstates, notations, I mean. But so this is a possible notation for the eigenstates of the quadratures. And the last thing is that one common type of measurements is homodyne measurement, where you project onto these eigenstates. Let's say the S. And of course, you can choose to detect no matter which quadrature. So you can also have here Q and the eigenstates of Q, and so on and so forth. Okay, so why do we want to study this? Because there are promising experiments that are appearing. So there are, in quantum optics, for instance, people are able to generate cluster states that we are going to define in continuous variable up to 1 million modes, where 1 million is not even a theoretical limit. It's just that the person stopped the acquisition, but they could have gone as far as they wanted. And they also generated super large 2-dimensional cluster states very recently. So I would make a list maybe. And this was optical wavelength. Then with microwaves instead, there have been results by the Yale group where they were able to encode a qubit into the quantized microwave field, and they were able to demonstrate a break-even point that a qubit encoded in continuous variable could live longer than the one encoded in the Transmon two-level system. So then I would say break-even. And also, there are promising implementation within optomechanics. So just to summarize, there is a lot of new developments to come in the field. So with Anton, we have been studying what are the elementary gates in qubit logic. So we are going to revisit the possible operations that can be implemented in continuous variables, and we are going to be totally device independent. So what we are going to talk about could work for any of these implementations, because we only care about bosonic modes and operators that then can apply to whatever frequency or hardware, basically. We are not going to care about that. So before defining, yes?
What's the importance of these 10 to the power 6 modes? I mean, by mode, do you mean like frequency could be a mode?
Yeah.
So that means that you could make entangled photons of 10 to the power 6 different frequencies.
Yes, in this experiment, the modes were time bin mode, in the sense that they were, so it was a cluster state created in time. Not all the modes were available at the same time. So the image that they gave on this, I don't know if you saw the Wallace and Gromit cartoon. You saw the one with the penguin that is chasing the Wallace and Gromit, and they are putting the rails of a train, progressively in time. Ta, 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 ta. So this cluster state that they did here is exactly the same, and they use this metaphor in the footnote. So it's something that works like this, where also they managed to build a cross correlation, and this is time. So at each time you're given a certain modes, and then you have to measure them. And this is just one bosonic mode that comes out of a cavity.
So these modes are somehow, I could think about it as how many qubits in a normal picture. Okay.
Yes. And this was Furusawa. So with time bin. But then there are experiments by Pfister and Traps, where they do have frequency modes. Mm-hmm. And they have 60 about, so a little bit smaller, but still. So here, and then here these modes are available all at the same time. But yeah.
So what is the pro of optomechanics in this instance though? Is it just because it's simple to fabricate experimentally and couple to a nonlinear
So this is still so new that there are not really answers, but one potentiality is that it might be easier to get nonlinearities that induce, I'm going to say now, non-Gaussian operations. So a little bit like with microwaves. But then with microwaves there are like strong losses, and with optomechanics there are proposals for steady state preparation of non-Gaussian states that are, even with dissipative preparation of highly non-Gaussian nonlinear states, say. So this is very, very promising, but I'm not aware of really experimental implementations at the moment. Like, yeah, many experimental implementations, but no protocols for what I know. Okay, so let's see first a list of elementary operations. And then we talk about universal set of gates. So let me make a list. We have rotations. So these are given by e to the, let's say, r theta is e to the theta, and we have q squared plus p squared over 2. And in particular, to make an example, r of theta over 2 is the so-called Fourier transform. What does it do? It's a rotation by 90 degrees in the phase space. So it means that if you have a coherent state here, the f of alpha is here. Basically, you're switching Q and P with this operation. And similarly, for other angles, you're rotating by a certain amount.
Should that be r pi over 2?
There is a pi. Yes. Thank you. Yes. And so formally, if you want to write how the Fourier transform looks like, what it does, it switches Q and P. So it transforms eigenstate of Q in eigenstates of P. 1 over square root of 2 pi, integral in the r, s, r, q, and this is s in P. And of course, F dagger does the same on the P eigenstate. Okay, then we have also, okay, here I've used, maybe this I can write here, that the overlap between the two states, Q, P is the wave function, the plane wave. And this is the same R. Okay, then we have the quadrature displacements. And we have these two operators, x of s, called in analogy to the Pauli matrix x, E s, and z of s, e to the I s cube. And then if you remember from, probably you have seen in quantum optics courses, that these are the generator of the translations. In the sense that, of course, I didn't write it here, so I might, I hope I will not get it wrong with the signs. But the idea would be that x s on s q will be s plus, okay, now it doesn't work because it's the same letter. Let's call it r. R plus S, and Z S on RP is R plus S P. It's probably correct even with the signs, I believe. You remember that this is the generator of the translation in P, and this is the generator of the translation in Q. Okay, then we have squeezing. So here, by the way, in terms of like interpretation, from here we go here with this, and with this from here we go here, for instance. Or okay, R plus P, so positive, but I have this. You understood what I mean? Okay, then we have the squeezing. So the squeezing operator is given by minus IS QP plus PQ over square root of 2. And what this does, if you have a state that it's like this, it's going to squeeze it. according to a certain direction that is given by this parameter and by a certain amount. So in this specific case, maybe one might want to use a different letter because this parameter can be complex. It has a phase. So the modulus tell you how much the state is squeezed, and the phase tells you in which direction you're squeezing. And then there is another one that is the share. That is also indicated like this. And this one is a bit more complicated to see what it is because it's a combination of a squeezing and a rotation. So I'm not going to attempt to draw.
Is it like a shear?
Yeah.
I mean, that's, yeah. But yeah, it's just a visualize.
Well, how to, what, like a, yeah.
It's like you go like.
Yeah.
Yeah, but I wouldn't know how to draw it. But okay, let's draw it later. Okay, so what I wanted to make you notice is that all these operations are given by quadratic Hamiltonian in QMP at maximum. We have the displacements are linear in QMP, and the rotation for a transform, squeezing, and the share, they are all up to quadratic. So they are all given by Gaussian Hamiltonians. So these are all called Gaussian operations. And then we can write already what is a universal gate set for Gaussian operations. Which is, so we can take, for instance, a displacement that I've been defining before, the share, the Fourier transform, let's call it F. Okay, and this is it. Now, let me introduce, to complete what we need for a universal gate set, let me introduce the first notion of CV universality. There are two. We are going to see the second one as well in the second hour. So we say that you can do universal quantum computation in continuous variable if you are able to implement any Hamiltonian that is an arbitrary polynomial of the quadrature QMP up to an arbitrary precision. And this is a polynomial. So this is what we want. And basically it turns out, let's say, up to precision epsilon. It turns out that with only Gaussian Hamiltonians, if we are going to shuffle them and repeat them many times, we are always going to take to obtain a Gaussian polynomial. So we are never going out of polynomials that are order of 2 maximum. So this is not what corresponds to the notion of universality. So to get to universality, sorry, I would like also to make another comment first. So I forgot one operation that I would like to write in another color. So let's put it in red. So this is also required. It's a two-mode operation, and it's the so-called CZ gate, which is a conditional displacement of a quadrature depending on the value of the other mode, of the quadrature in the other mode. And sorry, this is also Gaussian, so I should have said it before for this reason. But you can interpret that this is a universal Gaussian single mode. Then with this you obtain universal Gaussian which means any quadratic Hamiltonian. And now I was saying we need more, because otherwise we don't get arbitrary polynomials. So one ingredient that can be added here to get a universal gate set is the cubic phase gate. And it was shown by Brownstein and Lloyd in '99. So this is power 3. It was shown by, yes.
Sorry, it's a bit hard to see the colored markers.
Okay, I will never use them anymore. It's just that this is Q1 tensor Q2, and this is a Q to the power 3
Okay.
with a parameter S. So now this becomes universal. For CV QC, and this is a result by Brownstein and Lloyd. Of 99. So what they showed, basically, it works that if you have all these possible gates, then you can combine them an arbitrary amount of time. And by the commutator, so if you, you know that if you use like a Baker or Hausdorff type, so it's something like this that you use, that if you can implement these building blocks repeatedly, then you can also implement commutators. And what Lloyd and Brownstein show is that having one single non-Gaussian building block here allows you to obtain all the possible higher order by the commutators, basically. So you go out of the set of Gaussian operations. Okay, if you don't have questions on this.
So for CV computing, we need a total of 5 different operations to be universal.
With the first notion, then you will see in the second one, you need as many as the qubit ones.
Okay.
Yeah. Okay. Do you have other questions? Yeah, by the way, these are not redundant. The ones written there are really like a set that you really need all of them. Otherwise, you miss something. Other questions? This I'm raising, but remember, because we will more or less use it. Okay, so then we can jump to measurement-based quantum computation. Why? Because, as I said, since we have availability of 1 million mode cluster states that can be deterministically produced, it becomes kind of the natural paradigm, the natural model for CV computing. So then the first thing that we should do is defining cluster states. So we had the CV and the Q computation. Let's do measurement based. Okay, first the CV cluster states. You remember with Anton, you have seen that if you have a certain graph, okay, this is simple because it's a line, but say something like this with nodes 1, 2, 3, 4. Then in DV, you have your cluster states, and then you apply CZ operation if they are connected in the graph by an edge. So here we will have 1, 2, and then a CZ 1, 4, a CZ 2, 3, and a CZ 3, 4 in this example. And this CZ, they all commute to each other, so you can reverse the order as much as you want. So in CV is exactly the same, except that we start ideally by infinitely squeezed P state. So this corresponds, you remember that we have seen that these are the eigenstates of P. It means that if this is P, so the P line, so these are all the states that have like infinite precision in P. So these, they are lines basically. So we started by the one that is here, that eventually will become, in the finite energy case, it will become something like this. And then we apply the same recipe. So then we just have to do this.
So sorry, in the ideal case, it's infinitely squeezed along one direction?
P, in this case. So an ideal continuous variable cluster state is prepared by starting with as many infinitely p-squeezed states, as many the nodes of the graph, and then by applying CZ operations by those edges in the graph that are connected, by those, between those vertices in the graph that are connected by an edge, like you would do in discrete variable, with the CZ being the operation that we defined before. Okay, so now let's go to the measurement-based quantum computing scheme. We are going to consider the following circuit. We have our state that we want to process, and we attach it to an infinitely p-squeezed state via a CZ interaction. So this is the CZ. And then we are going to measure the P observable, which corresponds to homodiene detection physically. And we obtain an outcome S. Here let's call it M. So let's go in to see what we obtain here. We are going to calculate it.
Julia?
Yes.
In this CZ,
Yeah. Sorry.
is it just like you take qubit or mode 1 and mode 2 and just displace them? Because e to the iq is just a displacement in the q direction.
Yeah, then it depends on the state that you have. Typically, you are going to express, we can write it also. So if you have psi1, psi2, this is integral dq1 of psi q1 q, and then I can take the wave function in p for the other one. Then CZ of this is the most general case, would be the integral in dq1, sorry, there is an integral in dq1 and in dp2 of psi q1, psi p2, and then here you have e to the I q1 q2 that acts on q1 p2. So this is the first operator, it's an eigenstate, so this becomes a number. It becomes e to the I q1 q2 operator acting on q1 p2, and this is the generator of the translation. So this will be q1 p2 plus q1, and then you put this into the here. But we are going to do it actually. We are going to do a very similar calculation because we have it here, so we want to We want to do it explicitly for the case where one of the two is the infinity squeeze, p-squeeze state. So we are going to see the same thing once more. Can I erase it to have more space? In other words, let's do it again with our states of interest. Indeed, let's say that our input, our phi, it has a certain wave function. In these notations of the nodes is the same thing that I was writing before, but I use the notation of the nodes. So this is the wave function in the position representation. Then the input state on the two modes can be written as phi times 0p, which is the same thing that I wrote here, integral ds fs sq times 0p. This is before the CZ. Now we want indeed to implement the CZ. So we are going to do exactly what we did before. What we can do, okay, so here you see that I can use the fact that Q1 acts on this, that is an eigenstate, so I can replace with S. This first operator is the same step that we did before. And now this is the generator of the translation for this state. So then this becomes the integral in the S, f of S, SQ, SP. And now we use the expression that, so what we have to do, you see that here we have to measure in P. So from an eigenstate of Q, we don't know what happens if we measure in P. So we have somehow to express this in terms of eigenstates of P. And this is with the Fourier transform. So we have to say that this is the Fourier transform of eigenstates of P. So then this can be rewritten like 1 over square root of 2 pi integral yes f of s integral in the r s. So what we have used is that SQ is 1 over square root of 2 pi integral in the r s r p. So this goes here. Okay, and now we see that when you measure P and you obtain an outcome M, you're basically projecting onto the eigenstate M of the operator P. So you see that in this integral now, all the other terms that are not M disappear when we project onto the bra of the first mode. So this is going to select. I don't write anymore the constant because anyway we will have to normalize. But we obtain integral of the S, f of S, and then M. So we still have the factor with the M instead of R. And then, okay, this has disappeared somehow. And then we have S. So let me not write anymore the first mode. We are going not to, anyway it's a von Neumann measurement postulate, so once this is measured, it stays in M, nothing relevant happens there. So let me just forget about it. So now this I can interpret it. You see that we have the same S here and here. So this I can interpret it as if it was the action of the operator P on S because it's an eigenstate. Is it clear?
The term got dropped.
What do you mean?
So when you insert the definition of S in the Q quadrature in terms of the P quadrature, what happened to our CZ squeezing term in front?
I used the, so here
Where did it get inserted?
here I had Q1, Q2,
Yep.
and this is an eigenstate of Q1.
Yes. So that turns into S.
Yes.
And then we insert for the infinitely squeezed state
And
the definition in terms of.
No. I just said this is the generator of the translation of Q.
Yeah.
So then this becomes RP.
Yeah.
Sorry, SP.
Ah, okay.
I'm saying that e to the S Q2 0P is SP.
Ah, okay, I see.
Then this as a P, we leave it where it is. But we have to measure the first mode in P. And so far up to here it was expressed in terms of Q. It's like when you measure with qubits, that if you want to measure X and you have a certain state, you have first to transform it in a way that it makes appear eigenstate of X. So here we want on the first mode to appear eigenstate of P, but we have an eigenstate of Q. So we have to say that Q is the Fourier transform of P. So then here we get an integral. And then when we measure with the bra, projecting on the bra, we select one only of this R, which is R equal to M. And we are here. Then from here, you can interpret this as the operator, because S of P is an eigenstate of P. So then if you act on this, you can replace with S, so it works. It's a trick. So then this you can take out. And then, I don't know if you remember, but we had defined the displacements exactly like this. So then this I can rewrite like x of m. And then now we have, you see that we have the state integral in the S, f of s of, instead of having, so if it was the representation of the state, this, we would have S of Q. But we have S of P. So it means that this is the Fourier transform of S of Q. You can take it out. So we obtain at the very end that this is xm f of phi. So we can write it here, xm f of phi. And if you remember, in MBQC with Anton, you also got a Pauli, that was a byproduct, and a Hadamard, that was a byproduct. And then you got your state. So for the moment, it's a sort of very, very crappy implementation of the identity, because we measured P, and we got the same state that we had in input, apart from byproduct operators. So clearly is not the most general thing, but it's just to tell you that it's the most difficult step, and then all the rest follows from this. So now we can elaborate from here. So if you want, measuring P yields identity apart from byproduct operators. But now, how can we improve this? Well, if you send allocate the state, or transform the state, where this dq is a general operator that commutes with Q, so it's a function of Q of any order. Then you have, so this by the way is the integral in the S f of S of dq SQ. So then everything will go exactly the same. And this, if you allow me to do so, or I can draw a different scheme, it's better. Then this will be your state psi. Then here we have this dq, like a gate, our 0p, and then you measure p and you get n. So if we do this, what we get here is exactly, you can do exactly the same thing, except that instead of a phi, here in this this thing, you have the transformed phi, so it's a dq of phi. So basically you can write this as xm f dq of phi. But so far it's not very measurement based. The point is that this is a function of Q and this is also a function of Q because it's a CZ gate. So this commutes with this. It means that in particular, instead of having it before the CZ, I could have it here. So we are going to move it, and this is equivalent to measuring a rotated quadrature. So is equivalent like a transformed quadrature. Depending on the Q, it might not even be a quadrature. So this starts looking like MBQC. The idea is, suppose that you want to implement the operation dq on the state phi. Then what you do is you take your phi, you entangle it with the infinitely p-square state, and then you measure a transformed quadrature in this way. And what you get here is the action of this rotational transformation on your state apart from byproduct operators. So this looks more what we wanted to do. And now we are going to see what happens by concatenating several measurements. So suppose that you repeat the same thing twice. Now you have two ancillary squeeze states. And here you are going to measure the first time with dq1 dagger p dq1 and obtain outcome m1. And the second time with dq2 dagger p dq2 and obtain outcome m2. So what is the state here? Basically we know it already without calculating because it's about repeating twice this. So what we get here is xm2 f d1 q xm1 f dq1. Sorry, this was a split 2. Why? I think what? Let me check how much time do we have. Not much, but we can conclude. It's feasible. So now you remember that with Anton, you were also obtaining something like this. And then you were using some identities. So here we have exactly the same. Actually, the mathematics is remarkably similar. We are going to use the following fact. Which is just, since xm is given by this, it's just a sort of translation of the operator Q. And then, okay, you would also have analogously z minus m p z m, which is p plus m. And then you can also use that f dagger minus q, f is equal to p, and that f dagger p, f is equal to q. So I'm not going to do all the steps, but then using these identities, it is possible to rewrite the output state. Let's call it upside out. So this gets rewritten like x of m2, f x of m1, and then we have d2 power minus p plus m1 and dq1 dq1 on the state phi. So basically from here what you can learn is that if you just implement this paradigm, the output transformation is not deterministic, but it's random, because it depends on the measurement outcomes on the first mode. The second transformation remains affected by some randomness. So what you learn from this is that if you want to implement deterministic MBQC, it's like with qubits, you should adapt your measurement here, depending on the outcome that you obtain on the first measurements. So basically here, if instead of that you would have measured in a transformed basis, so let me define, by the way, this object. Let me define it like P with f of q, where you know that dq has this f of q here. So basically here, if instead of measuring like this, you measure with d, so sorry, p f of minus q minus m1, then this will become deterministic and it will become your d of p. So this is to say that in general, you should measure something that depends on the outcome of the previous mode if you want to implement a deterministic MBQC. Then we should take a break. I just didn't manage to, the very last thing that I didn't manage to tell you, it's quite important actually, is that in the specific case where this dq is up to quadratic order, so order 1 or 2, this polynomial function, this adaptivity is not necessary, because it becomes trivial that you can measure the same observable, namely homodyne, and then add some post-processing correction. And I think this was also the case with Clifford operation. So in this sense, the Gaussian operations, where the Hamiltonian are up of order 2, so either linear or quadratic, you don't really need to adapt this measurement, like for Clifford operations for qubits. And the second other thing that I wanted to mention, like with the MBQC for qubits, you could think that you can extract this. Suppose that you do many of these operations, then you get many of these states. Basically what you have is a cluster state, because all of these CZ, they commute with each other, and so you get, out of 0p and CZ, you get a cluster state. So this is like having a state that is attached to your cluster state, and then you measure the nodes locally. So this is really what you're seeing for qubits. And I put all the details of this triviality of adaptivity for Gaussian measurements in the notes, so you can take a look. And we stop here for the break.